Okay, hello everyone. So we're looking at derivatives now in a little bit higher dimensions from R2 to R3. So this means we're going to have like two directions to go to. We're going to have E1 and E2, and we could move in either of those ways in the input space. And when we move in the input space, what happens in the output space? So that's what this question is about. So part A, explain how curves of unit velocity E1 and unit velocity E2 become curves on the surface. And with what velocities do those curves have? So my answer to part A looks like this. This is my answer. You see it has two pictures, it has some words. Actually doesn't really have formulas because this question is not about a specific map. Like I didn't actually tell you what is this map. We could parameterize a sphere with a map like this, but I didn't give you a formula for this map. So this would be a pretty complete answer. It says that the map F, it maps the entire plane so that it also maps horizontal and vertical lines. So this purple line and this green line, that purple line becomes this purple curve. That green line becomes that green curve. And so this was my first observation, is the lines in the plane are also mapped. F maps the entire plane, so it maps the lines. It maps all the points on those lines to points somewhere in three-dimensional space. Okay, that was the first observation. And I gave pictures. Oh, and words. Now, the second observation is, this shouldn't be there. Okay, the second observation is, if I run or move along those input lines with unit velocities, E1, E2, so here's my picture of that, the purple velocity and the green velocity, then I could also run along the curves, and then my E1 becomes this purple df at x applied to E1. All right, so this is the derivative of f at the point x. That's a linear map. We're going to apply that linear map to this vector, this E1 vector. And what we get is a vector in R3, this purple vector. Okay. And actually, I mean, what we'll see is that, if this was an orange square, then the nonlinear map takes that orange square to some sort of curvy orange thing on the surface. But that was the map F. So the map F takes that square there. But this square under the map df at x, this is a linear map. So this map will take that square to a parallelogram. It'll take it to a parallelogram flat. So that's what this map does to it. Whereas the other map took it to some sort of curvy piece of the surface. That was the map F. Did this. Okay. Let me get rid of that because that's not really part of my answer. I'm just talking too much. So that's it. So I just said become curves with velocities here. So I answered it. What velocities? The question. These velocities. And that's my answer. With what velocities become curves on the surface. I explained it with a picture. Okay, now let's look at part B. Using linearity of the derivative, explain how a curve in R2 with velocity v, now I'm not taking these special velocities, these easy velocities, but some random velocity curve in the input space with velocity this vector. Well, that should become a curve on the surface under the map F. And now the question is, with what velocity? Okay, that's part B. Okay, this input velocity becomes a what output velocity? Here's my answer. This would be a complete full credit answer. Well, since any v in R2 is just a linear combination of those very special ones we looked at in part A, there it is. Then because this map, this derivative map, is a linear map, it takes this linear combination to a linear combination of these special ones from part A. And so as soon as I know these, I know everything. In particular, V sort of looks like it's 1.2 of E1 and 2.2. So V might be 1.2 of E1 plus 2.2 of E2, maybe, or 2.3. I don't know. It's at least 2 of E2. Okay, then what I do is I go 1.1 of this, and then I move 2.3 of the green. So I do 2.3 of the green. Anyway, my picture's not super great, but you just do the same linear combination of this purple and this green. Okay. So I'm gonna try to get rid of all this orange. Therefore, an import curve with velocity v becomes a curve on the surface with velocity this. And that's my answer. And I explained it. I used linearity to explain it. Here I did actually some calculation with formulas. These weren't very specific formulas. They're sort of abstract formulas. They work for any map f, even though I don't even know what the map f is in formulas. I still have, it's a name for its derivative, which I could then compute later. Okay, that's my answer.